thank Pierre and the organizer for the invitation and for giving me the opportunity to present my work. So today I'm going to talk about optimal control theory and some applications in spin systems and in magnetic resonance. So this work is a joint work with my group and my colleague Stefan Glaser in Munich. So I would like also to thank all my fundings, so both in France and in Germany, in Munich. And so here is the outline of my talk. So after a first and brief introduction to quantum optimal control theory, I will give you two different examples, two different approaches to design some control fields, so to control two-level quantum systems. So the first one based on a classical effect, so the tennis racket effect, and the second one based on optimal control theory. And I will finish my talk by describing recent applications in magnetic resonance imaging, so with the contrast problem. So first, some words about optimal control theory. So it's a very general mathematical framework where the goal is to design a control field which allows to reach a given target state while minimizing or maximizing a figure of merit or a cost functional. So here I give you the example of a Rubik's Cube where we start from a random Rubik's Cube, and the goal, for instance, is to reach in minimum time a regular one. And so now optimal control theory is very well known in mathematics, and this theory has a large number of applications in different fields in physics or in economy, biology, and for us in quantum physics. And I will also describe this example in medical imaging. I would like also to mention this review paper that we wrote with, so I don't remember, maybe 11 or 12 colleagues, so in 2015. And in this review paper, so we give, so maybe more than 500 references about quantum optimal control, and we also describe so the different goals of quantum optimal control at short, middle, and long term. So I think it's a good way to enter into this field and to know the last references in this field. So the idea of using control pulses in quantum physics or in spin or for spin systems, so it's not new at all. So I think that maybe so physicists and chemists try to control spin systems so since the 50s. So we can mention different approaches, so like the adiabatic pulses, the composite pulses, or the Shinnar-Leroux method. But all these approaches are some qualitative methods in the sense that so they can be very efficient in some cases, but in general they have a limited efficiency. So in the general case, so that's why, so basically in the 80s and 90s, so people in this field tried to introduce more general mathematical approaches, so like optimal control theory in particular. So one goal was to reach the physical limits of the dynamical processes that they consider. So for optimal control, I would like also to stress that, so in my opinion, so there are two different ways to attack an optimal control problem. So the first one that we can call geometric approach, if n, so n is here the number of degrees of freedom of a system. So n of the order of 1, so means a very simple model, so an ideal system. And basically, the idea of a geometric approach is to try to solve with some analytical expression or geometric tools the optimal equations. And in general, so we can have some information about so the global optimal solution or the physical mechanisms or the physical limits of a process. And in recent years, so many different problems so were solved by using this approach. And the other one is so numerical approach, so for more complicated systems. So here basically, so the idea is to use some optimal control algorithms to design numerically an efficient solution. So one advantage of this approach is its flexibility. So we can use this approach in many different situations. So we can take into account some experimental constraint and experimental imperfections. Okay, and so now in the first 2 parts of the talk, I will focus on the geometric approach, and I will give you an example of a numerical solution in the last part of the talk. But so another important point, key point to mention about optimal control in quantum physics and for spin dynamics is the fact that in general we consider some open loop control processes. This means so without any feedback. And in this case, the accuracy of a model system is a key point, is crucial. But so in general, in a realistic control problem, so in a standard experimental setup, so we have to deal with some experimental imperfection and model uncertainties. So that's why we have to design some very efficient control pulses, but also pulses which are robust against some such experimental imperfection and inaccuracy of a model system. So that's why also, so people used adiabatic pulses, composite pulses to try to design such robust solutions. But in my opinion, so here again, optimal control theory is so the most efficient tool to design such pulses which are both very efficient and robust against such imperfections. And the last point of this introduction is about a kind of mathematical definition that we can give about so the robustness. So it's maybe not the most general mathematical definition, but is in general the definition that we use in physics. So we consider an ensemble of quantum systems depending on a parameter delta, and this parameter, so it's the unknown parameter, delta belongs to the interval minus delta 0, delta 0. And the goal is to use only one control field, so the same control field for this ensemble of quantum system, such that so the fidelity of the figure of merit, which is so its maximum value, so for instance it's the value 1, so for any value of delta in this interval. So we can distinguish 2 different definitions, so a local one where basically we try to vanish the different derivatives of j with respect to delta. So here, for instance, the first derivative is equal to 0, the second one in green, and the first 3 derivatives are equal to 0 for the red curve. So it's a kind of local definition because we improve the robustness around the value delta equal to 0. So in general, so we can also use a non-local definition in order to increase so the range of robustness by considering a discretization of so the unknown or the inhomogeneous parameter delta. And for instance, we consider some specific values for delta, so delta 1, delta 2, and delta 3, and so on. And for this finite number of values, so we try to maximize j. And then, so it's just a numerical adjustment, so we have to choose so the discretization step that we use to select the different values of delta. Okay, so now, so after this short introduction, so I'm going to focus on the first example, and the idea here is to use a classical mechanical effect, so the tennis racket effect, to show you how to design some control pulses in a 2-level quantum system which is robust with respect to some experimental imperfection. So first, I start with a description of this geometric effect. So the first point to know, so it's a very well-known geometric effect which can be observed in the free rotation of any three-dimensional rigid body with some asymmetry. So one example is given by the tennis racket, and it works very well with any tennis racket. So basically the experiment is the following. We have a tennis racket with two different sides. So for instance, here we have a red and a white side, and the white side is facing up. So we take the tennis racket by the handle and we throw in the air, so like that, so the tennis racket such that the handle makes a 2 pi rotation. Okay? Then, so we catch the handle and we observe in many different situations, so for many different initial conditions, that so we observe a flip of pi of so the head of the racket. So this means that when we catch at the end of the process, so the handle of the racket, so now is so the red side of a tennis racket which is facing up. And this beautiful geometric effect has been used, for instance, by Richard Cushman and Larry Bates as an illustration for this book on classical integrable systems. So now, to give you a mathematical description of this classical effect, so I have to introduce some Euler angles. So here we choose a set of Euler angles, so theta, phi, and psi. Capital X, capital Y, and capital Z represent the different directions of a laboratory frame. And E1, E2, and E3 are the frame attached to the racket. So basically, E1 is along the handle of the racket. E2 is here. So E2 is orthogonal to E1, but in the plane defined by the head of the racket, and E3 is orthogonal to the head of the racket. And a simple way to observe the tennis racket effect is to take theta of the order of pi over half, of pi half, and in this case, so E1 is in the plane xy. So for the tennis racket, so we have to consider a variation of phi of 2 pi, so a turn in the xy plane. And during this motion, so we observe this so flip of pi, so for the angle psi. So it's a very simple description of the tennis racket, so in terms of the Euler angles. And we can also write some differential equations, so the well-known Euler equations. So here M1, M2, and M3 are the coordinates of the angular momentum in the frame, in the moving frame, so in the frame attached to the racket, and I1, I2, and I3 are the different moments of inertia, so I assume that I have an asymmetric rigid body. So we have also, so we can find two constants of motion, so the system is a classical Hamiltonian and integrable system. So the same equations can be also written in terms of the Euler angles, so theta, phi, and psi. So it's very straightforward to get these differential systems. And so here I introduce some new parameters, so A, B, and gamma, which can be expressed in terms of I1, I2, and I3. And now, so we can plot a very simple picture to understand so the tennis racket effect. So is this phase space So it's a reduced phase space in terms of psi and psi dot. And here, so I take the derivative of psi with respect to the angle phi. So in other words, so here phi plays the role of time. And so in this reduced set of coordinates, so we get a very simple phase space. And this phase space is similar to the phase space, for instance, of a two-dimensional pendulum, where here, so we get so the oscillating trajectories and the rotating trajectories in blue. And we have also a separatrix, so at the border between the two families of trajectories. And the only difference between a standard pendulum and the tennis racket effect is the fact that between so the difference of angle between the two unstable points, so this point and this point, is equal to pi, whereas so we have 2 pi in a standard pendulum, in a standard two-dimensional pendulum. And this simple observation is at the origin of so the tennis racket effect. Because now, so if I consider a series of classical trajectories with some initial conditions close to the unstable point, then we observe, so just by computing so the different trajectories, we observe that for all the trajectories starting close to this point, then so we observe a delta psi, so a variation of psi of the order of pi. So it means that to observe the tennis racket effect, so we have to consider a classical trajectory which is very close to the separatrix. And so due to this difference of pi, so that's why we observe so the tennis racket effect and the flip of pi of the head of the racket. And so one step further, so now it's for the moment it's just a numerical observation, but we can prove so the robustness of the tennis racket effect. So we can have at least an estimation of this robustness with an asymptotic expansion of epsilon. So epsilon is just a parameter which describes so the defect with respect to a perfect tennis racket effect. And so we see at first order that epsilon is the sum of two terms. So one term which is connected to the shape of the body. So basically if we have a perfect asymmetric body with a very large difference between the different moments of inertia, then the product AB goes to infinity and this term goes to 0. So it's the first term, and we have also robustness with respect to the initial conditions, because here basically gamma is the distance to the separatrix. So it means that we have to be very close to the separatrix to observe a twist of the order, a flip of the order of pi, and to have a defect epsilon very close to 0. So this mathematical description, so established so last year in my group, is the last point of the classical description of this effect. And now I can focus on the design of the control pulses for the two-level quantum system. And so the first question that we have to ask is the following, is how to translate this property into the quantum world. Because for the moment I only describe some classical objects. And the idea here is very simple. So the idea is just to use the formal equivalence that we have between the Euler equations and the Bloch equations. The Bloch equations which describe so the dynamics of a Bloch vector. So here m in this in the Euler equations, m correspond to the angular momenta, and here so here m correspond to so the Bloch vector. And so in the Bloch equation, so omega 1, omega 2, and omega 3 are just, for instance, so in nuclear magnetic resonance of the different components of a magnetic field that we apply to the spin. And now, if we make this identification, so between the different components of a magnetic field and so the coordinates of the angular momenta divided by so the different moments of inertia. So we have a perfect identification between the two dynamics, and so we know exactly so the trajectory, because the trajectory of a Bloch equation will correspond exactly to the trajectory of a rigid body. So it's a way to design the control fields and to find some analytical expressions for the trajectories. And here, so it's just a comment. So in general, experimentally, so only two fields are available. So we have to play with the different moments of inertia, which are some three parameters that we can adjust. So in the Bloch equations, just to have only two coordinates or two control, omega 1 and omega 2, and we take, for instance, I3 equal to plus infinity to have only two controls. But so the arguments are exactly the same in this case. And so we have, so the moments of inertia, so for the Bloch equation are some three parameters that we can adjust, and without loss of generality, so we can choose I1 equal to 1 and I3 equal to 1 over k squared. And so with this parameter k, so we can recover so the standard optimal solution, for instance, for the transfer of the population from the ground state to the excited state, so for a two-level system. We recover in the limit k going to 1 to the adiabatic pulse. So for the separatrix, we recover the standard Allen-Eberle solutions. And we can also show, if we consider so this test, so this evaluation for the robustness of a control pulse, that the robustness of a process is connected to the value of k. So basically, so by increasing k, so we can step by step we can increase the robustness of the process. So here we have a perfect robust process with a figure of merit equal to 1. So whatever the values of delta and alpha are. But so here we are exactly in the adiabatic limit, so that's why you obtain a perfect robust process. But so we have, so we can understand with this analytical description the transition from a pi pulse to the adiabatic pulse. So I finish here. So this second part, and now I'm going to focus on another application, that is the application of geometric optimal control theory. So here again, for the design of robust control pulses for two-level quantum systems. So here, the idea is to apply directly the Pontryagin Maximum Principle. So here, I just recall the principle of a PMP, of a Pontryagin Maximum Principle. And the idea is just to know that finally the idea of a PMP is to transform so the initial control problem into a pseudo-Hamiltonian control problem, or a pseudo-Hamiltonian problem, where the goal is now to design or to find the right trajectory going from the initial state to the target state in a given time. So here is so the definition of a Pontryagin Hamiltonian. So where P and P0 are the adjoint state, and so we know that the PMP so gives only some necessary conditions to be optimal, with the following maximization conditions, where U is the set of admissible control that we can consider in a given example. So my goal here is not to enter into the details, but just to show you that it's possible with a PMP to design some robust control fields up to a given robustness order. And for that, so we consider the Bloch equation with two unknown parameters, alpha and delta. So delta, so it's basically so an offset imperfection, and alpha is a scaling factor, so due to some imperfection on the control field. So here we have two control fields, ux and uy. And so for instance, if I consider only one unknown parameter, delta, so I have the following perturbative expansion of q as a function of delta, where q0 is the homogeneous part, and q1 and q2, so the different terms of the perturbative expansions. And now in this is new coordinates, so q0, q1, q2, and so on. So I have, for instance, for the transfer from the ground state to the excited state, so I have for q0 this initial state and this final state, and for q1 I start from 0, 0, 0, and I have to arrive to the same point for q1, q2, and for the other perturbative terms, just to be robust. So we can rewrite the Bloch equations in terms of q0, q1, and q2, so by introducing some new matrices. So, and now it's just some mathematical derivation. So we can write the Pontryagin Hamiltonian in this case. So it's quite complicated, but we can introduce some angular momenta like coordinates and some and the sum of such angular momenta. So it's some coordinates. And so the interesting point is the fact that at the end, up to a given orders of robustness, so for instance here n is the robustness order, so we obtain a closed systems. And if we are able to find so the solutions of this system, so then we are able also to find the optimal control fields, ux and uy, and with the optimal control fields, by plugging such control fields in the Bloch equations, we are able to compute the optimal trajectory. And just to summarize, so with the application of Pontryagin Maximum Principle, we start at the beginning from an infinite dimensional control landscape, and with the PMP, so we transform this landscape to a finite dimensional landscape. And so we can show that so this dimension is equal to 2n when we consider a robustness up to the order n. Okay, and so in general, so at least up to the order 3, so we can find the global optimal solution. So in general, analytically, so for the order 1 of robustness and for the order 2, and we can estimate with a very good accuracy, so the global optimal solution for the order 3 of robustness. So here are some solutions that we obtain with the PMP. So here is on the left is with a local definition, and on the right with a non-local one. And we see that so here in dotted line is just the pi poles, and we obtain so in blue the order 1 of robustness, in green the order 2, and in red the order 3. So here is an example of so the optimal solution. So here are so the control field. So here we assume that we have only one control field and the other one is set to 0. So the second one in green. And here, so it's so the shape of the different control fields. And in this case, so we are sure, so at least for the two first orders, that this solution is so the global optimal solution of the problem. So this work can be done in different cases. So for the time minimum solution, for the energy minimum solutions, so for the local and the non-local definition of a robustness. And finally, so we arrive to a table like that, where we give, so for the first and the second and for the first three robustness order, for instance, the minimum time that we need to control exactly so the spin system. And so this result, so I think it's very new, and it's the first time that such global optimal bounds are derived. And now, so one open question is the following: is it possible to extend this approach to higher orders? So for the moment, so we are able only to solve numerically this problem up to the order 3. And so one question is it possible to solve this problem for the order 4, 5, or 6, for instance? So I'm going to skip this part. Yes, because so I would like now to talk about one application in medical imaging of optimal control theory. And so the idea of this application is to show how we can combine the advantages of the two different approaches of optimal control theory. So that is so the geometric one and the numerical approaches. And for that, so we consider a standard problem in medical imaging, so in magnetic resonance imaging, which is called the contrast problem. And basically, so we have the following experimental setup. So we have two different tubes. One tube, for instance, the inner one is filled with one spin or one species of molecules, and so the second tube, so the outer one, is filled with another spin. So we apply the same magnetic field to the two samples, and the goal is to find so the magnetic field which maximizes the contrast, so the difference of colors between the two tubes. So here, for instance, in this cut, so we obtain a black color, so for the tube here, and the goal is to obtain so the best white color or gray color so for the other tube. Okay, and optimal control theory can give us an upper bound for this maximum contrast that can be achieved. So first of all, we can consider the ideal situation so by using geometric optimal control theory. In this case, so we consider so there is no experimental imperfection, and we consider two uncoupled spins corresponding to the two tubes. So the first spin with the label 1 and the second spin with the label 2, and the two spins are subjected to the same magnetic field, so here UX, but so the dynamics of the two spins are different due to the different relaxation parameters T1 and T2, which are different for the two spins. So here we consider the example of desoxygenated blood and the oxygenated form of the blood. And the goal of the control problem, so if we fix the time, is to reach, so for the first spin, for instance, the center of a Bloch ball, while maximizing the modulus or the square modulus of the second Bloch vector. And here, so I plot the solution that we obtain with geometric optimal control theory. So we have some analytical expression for the different control fields. And we see that, for instance, here in this case, so the two spins start at the thermal equilibrium, so at the north pole of a Bloch sphere. And so the first spin reaches the center of the Bloch ball, and we maximize the distance at the end of the control between the two vectors, the two Bloch vectors. Okay? So this case is, so this solution is only valid in the ideal case, and in practice, so we have to deal with some experimental imperfections. So basically here in magnetic resonance imaging, it's some magnetic field inhomogeneities. So the interesting point is that we can have a feedback from the experiment in the sense that we can measure the spatial distribution of B0 and of B1, so the two magnetic fields that we apply to the sample, and we can use so the two distributions in the numerical optimization of a control field. So now, so we cannot consider only two spins, but an ensemble of spins, so with different parameters, omega and alpha, so different inhomogeneities, and omega and alpha basically depend on the spatial position of the spin, so capital X, capital Y, and capital Z. So then, to have a finite dimensional control problem, so we use a regular discretization of the two parameters, and with a numerical adjustment of a discretization step, plus some few hours of numerical computation. So we obtain with a standard optimization algorithm, so the following solution for Ux and Uy, and here, so here is so the numerical simulation of a contrast. So we obtain so the best possible contrast, and here is the experimental result. So we have, so thanks to this feedback between the experiment and the theory, and the fact that we take into account the different magnetic field inhomogeneities, so we have a very good match and a good agreement between theory and experiment. So this result were obtained so in Munich in 2012, so if I remember. So but it's just an in vitro experiment. And last year, so we apply the same principle to this time an in vivo implementation of optimal control theory. And so we consider the brain of a mouse. So the brain is here. And the idea, the goal of the control was here to maximize so the contrast between so the brain here and that we call the parietal muscles, which are so basically so the muscles which are around so the brain of a mouse. So here is so the result that we obtain so without optimal control preparation, and here we apply optimal control theory to maximize this contrast. So the goal is to saturate to obtain a brain which is black and with some white parietal muscles. So here. And we obtain that, so a very nice result. So here again with a very good agreement between theory and experiment. So the only problem that we have is this white dot. So this white dot represents in the brain of a mouse, so that we call the cerebrospinal fluid. And so it's a specific area of the brain which has different T1 and T2 parameters. So that's why because in optimal control theory, so we take only into account so the T1 and the T2 parameters of the relaxation parameters of the brain. So that's why. And T1 and T2 is almost constant in the brain, so except for this point. So that's why this point appears white, and so the other part of the brain is black. So it's due to this difference between so the relaxation parameters in these two areas. And so I will just so finish my talk with some conclusion and some perspectives. So we have shown how to design some robust control protocols by using either some geometric tools. So an example is given here by the tennis racket effect, or by using some optimal control principle and the Pontryagin Maximum Principle. So we have obtained, at least for the first robustness order, the global optimal solutions. So for the minimization of the time, or the minimization of the energy. So we have shown that we can apply so two different types of approaches, so the geometric and the numerical ones, and that this kind of approach can be used in a very complicated problem, so in MRI, so at room temperature, so for improving so the contrast of the brain of a mouse. And here, so it's a series of papers on the different subjects that we published last year. Yes, and thank you very much for your attention.